Hello everyone, I'm Hema Reddy. I've been with IBM for about 6.5 years now. Have been working on cell processor for close to 1.5 to 2 years. Moved over from System I and P series. I used to write device drivers and firmware microcode, and then just took a position with programming on cell processor. That being said, I'll just quickly go over what is exactly included in the development kit. Right now, this is the most accessible vehicle that's available to everyone because not everyone has a cell blade, and I think the Sony PlayStation 3 is not available yet in India. So if you have to buy it over here, I guess you have to go to eBay or something like that, and God forbid if something goes wrong, there's no help or support. So far, Sony or Toshiba have not committed if the plans are going to change or what. So the only form factor that's available in India would be purchase of a blade. That's a QS20 product offering from IBM website. So meanwhile, before then, if you wanted to get your feet wet, we have a very useful kit, that is the development kit that's available via the DeveloperWorks website. The links that Duke showed earlier in his presentation. The reliability of these results is very close to an actual cell blade, up to 99.99% accuracy. So in other words, if you have some code that is compiled to be built on the cell system simulator and you're getting some performance results out, it cannot be a big application because obviously the cell system simulator can only take you so far, but just to test out some general routines, algorithms, the results are pretty accurate. When you take the same code and the same executable and you run it on the cell blade, you can get comparable results. And talking of cell blades, we do have something called virtual loaner program. So if you are curious in testing out your code, if you have some algorithm that you want to run it on a cell blade, then do get in contact with us. We can get you set up with the loaner program so you can get a taste of how the hardware runs. So today I will be covering the development kit and also some basic programming concepts, some communication mechanisms on cell, why it's different from other, say, Intel multi-core architectures, the strong points, and some synchronization mechanisms. Obviously, when there's communication involved in a real application, there will be some synchronization overhead, so we'll go over that. And that followed by some examples on the cell system simulator in the programming hands-on session in the afternoon. The development kit has support for x86. So if you have your Linux, it doesn't have support yet. There's no tool chain yet for Windows development. So the limitation is that it has to be Linux, x86, 64-bit operating system, or any PowerPC box. It's got support, it's got lots of software libraries. In the afternoon, we will be going over the directory tree structure for the simulator and see where everything is, what are the libraries currently there. There's lots of workloads that have already been optimized. So when in the afternoon when you have your systems in the lab, you can look, there's quite a few workloads that have been optimized, so we can take a look at what the cell code looks like. Okay. It's got some support for some profiling tools, debug tools. Recently with this SDK 2.0, we have released an Eclipse-based IDE environment that makes it a little more GUI-based. So for those of you who are more comfortable with GUI-based development, there is an interface available that you can use to your advantage. Talking of libraries, there is a few SIMD math libraries for some math functions. This is something that was not there earlier that we recently added on. There's some already tuned functions, some trigonometric functions, some other math functions that are available that you could just directly link to and use them, invoke them in your code. There is a feedback directed program restructuring tool that will be going in further detail, in great detail actually tomorrow. So the typical process is on the system simulator, you build an application and there is a utility that allows you to take that application from your development sandbox over to the cell system simulator. It's a local loopback mount feature that you can use to take the executable from your development sandbox, and once the system simulator comes up, it is actually creating a virtual cell blade environment, and you can copy it over there. It's as simple as just copying it over there and running it. Supported languages are C, C++, Fortran compiler, we're not completely there yet. The Fortran compiler is in the works. It's not released yet, it's not stable yet. And an assembler. And there's a full-fledged GNU toolchain. It's a standard, it's like a GCC toolchain except that it's been modified to include support for cell hardware. Therefore, you would see PPU GCC, PPU G++ for C++ code. PPU 32 would be for 32-bit configurations, 32-bit Linux. And there should be a PPU 64, but I believe maybe in SDK 2.0 it's been linked directly. The default is PPU, GCC would be PPU 64. There's C++ language extensions that we can take a quick look at the header file after this presentation is over. That's a heavily used one. Anytime a standard code, simple scalar code needs to be converted to a cell code, there's a list of instructions. For example, instead of doing the plus add, you have to use the instruction SPU _ add. So all these instructions are mentioned in the API. It's a very simple user-friendly API that we can take a quick look at after the presentation. This is our application binary interface and an instruction set architecture. ISA, all of these documents are very easily available on IBM Microelectronics website. And in general, like the regular LD tool, AS utility, with any development environment, whatever tools are there are available for cell. The XLC compiler is an IBM proprietary compiler. Now it includes support for cell. The advantage, the reason there's two compilers, GCC and XLC, for cell is GCC doesn't have a lot of optimization support. XLC has got a lot of different levels of optimizations, 01 through all the way through 05. And 02 onwards, there's some automatic optimizations that get into effect once you build with that optimization flag. Automatic loop unrolling, introduction of no ops, code restructuring, function inlining. Some of these things happen automatically, and therefore if you're compiling some code in the cell software development kit on your x86 box, if you compile it with GCC, you see the performance numbers, and we'll go over all those in the lab sessions, and you convert it over to XLC and try to just use the same code with XLC, that you're bound to see some performance gain, assuming that there's no false dependencies in the loops. Okay. There's two different kinds of simulation models mutually existing. One is functional only simulation for code development and debugging. Again, we'll go over all these in the lab sessions. There's extensive tools available for performance simulation also. In other words, you can look at the queues, you can look at the pipelines, you can look at the performance statistics. In other words, after you run a simple program, how many cycles did it take? What is the CPI, cycles per instruction count? How many stalls were there? How many latencies were there? All those things come up in a nice graphical interface that will allow you to evaluate your application and see what are the performance roadblocks. The SPE Runtime Management Library gives the support for all function calls that allow you to create threads. When I say thread, the main, as Duke went over this morning, the PPEs and SPEs mutually coexist. There's a reason why SPEs or SPUs are called synergistic processing elements, right? Why are they synergistic? Because PPE is basically just a control-intensive processor. It cannot be used as a workhorse for number crunching algorithms. The SPEs are the workhorses. So all the PPE does once your main application starts is the main application resides on the PPE. It looks at the data buffers, and then PPE controls creation of all these. There's 8 SPEs that you can use to your benefit. So PPE will create threads, 8 threads, and if it's a full cell blade with 2 cell processors, 16 SPEs. So you can create up to 16 threads. So the PPE cannot basically do computationally intensive tasks. It's good at control intensive tasks and control task switching. the SPEs are more adept at handling, say, very tens of millions of loops, repeated computations, but they cannot run an operating system on their own. So the PPEs need SPEs and the SPEs need the PPEs, but they both mutually coexist, and so SPEs are called what they're called, which is synergistic processing elements. So there's a few runtime API that this runtime management library supports. The question was how much of the task, how much does the programmer have to take responsibility when it comes to creating these tasks or assigning tasks to these numerous processing elements, right? So the answer is good and bad. A lot, if you're a bare to metal programmer, a lot of control exists in the hands of the programmer. So in other words, you can decide if it's an image processing algorithm, say, for example, and there is 3 different stages to it, and you want 4 SPEs to work on one stage. So you know that your application is using up 4 SPEs. You are left with 4. And you can use, for the second stage, if there's no dependencies between the first and second, you can use another 2, because you know that this task does not have a lot of data to be split up and code to be split up between the 2 SPEs, and also probably there's no dependencies. So use 2, and then for the third stage, use 2. Now that load balancing responsibility, assigning tasks, splitting the data up, moving the data to the SPEs, all is in the hands of the programmer. So unfortunately, yes, there is a lot of responsibility. There's a lot of design issues also to be considered. So more time spent on doing these observations, data movement, locality of data, dependencies, everything, the better it is once the code is executed. That being said, we are continuously working with tools vendors, also internally in-house development of tools that takes these responsibilities away from the hands of the programmer. A lot of times in the industry, people just want to write quick high-performance program applications, but don't really want to deal with, oh God, I have to create memory, I have to send it over there, I have to make sure that it reaches, and then I have to write it back to the main memory. So there are some tools. One example is a RapidMind development platform. We have joined hands with RapidMind development platform. They are a new company, but they are rapidly, they have ensured quite a few VC-backed funding, and their programming model is basically one program fits all processing elements. In other words, the same code can be run on GPUs, say, the same code, if you take the code and move it over to cell processors, it'll run just fine. Move it over to some Intel multi-core architectures, it'll just run fine, and you don't have to change the code. On top of that, what the platform does is you can use your same development sets. You don't need to change your compilers. All you need to do is link with their library and convert your code into their RapidMind development platform APIs. So in other words, use their structures to create arrays of data and things like that. It has got a backend detector, which basically evaluates the platform to see what hardware it is, and at runtime, it just makes sure that the executable is converted to that format to run on that hardware. Also, the fact is they take care of splitting up data. The platform is based on data level parallelism. They automatically do the optimizations. So you don't really need to take care of any kind of memory DMA operations, any synchronization issues, nothing. You just take your scalar program, use their data types. You don't even have to parallelize it. Obviously, there are some things that you have to keep in mind, things like structuring of data. There's a way that you define the arrays and initialize the arrays so that parallelism is possible. So things like that have to be kept in mind, but it makes programming one notch easier. And there's another platform, Jude, that also helps. So SIMD math library has got some math functions that you can use. There's another library, Mathematical Acceleration Subsystem Library, which is an IBM proprietary library that was initially supported in BlueGene and AIX, and now it has support on CellBlade 2. It's just been released. There is a prototype version out there. But again, for those of you who are involved with HPC applications based on use of a lot of math functions, please feel free to try this library out. So the libraries are, they have both vector and scalar functions. They are thread safe completely, support both 32 and 64-bit compilations. And in order to use these functions, all you need to do is just link to the library, and you should be able to use all their APIs. And these are the samples packages that are there in the system simulator. We will go over these in the lab sessions where all these workloads are. For example, if you just want to see how the FFT workload looks like using the cell API, there is a workload already there which is tuned and optimized to be working on a cell blade, and it's gotten very good impressive results, and the benchmark slide that Tuk just went over. There's a sample image processing code. There is a newly included software managed cache, which is a very useful library. Basically, it gives, using this software managed cache, there is a few workloads that IBM demoed out at different conferences. We can show you a few demos. We have it on our laptops. Sometime in the afternoon, maybe we can kick off with some good demos. And again, all these workloads are there in the system simulator for you to take a look at with the source code. Samples has again some sample code. The performance utilities, we will go in detail in the about SPU timing tool, how it is used for static code analysis. Currently, the output that it produces involves a lot of assembly. So if you're not from an assembly background, it might be a little hard for you. But then the option is VPA, the Visual Performance Analyzer, that Duke will cover tomorrow. That will give you an option to see the source code along with the disassembly. Cell ID is just based on the Eclipse development tool. So this is pretty similar. It's just added support. It's the same Eclipse IDE. It's just got support for cell development too. So in other words, you can write code and build your application on the IDE itself. And it's got support for debugging also. So it's a standard, the same GDB interface, GDB tool that's there for more common Linux OSs. The same commands, the same syntax for triggers, breakpoints, listing of variables, all is the same. Okay. These are the installation requirements when you're ready to install the cell development platform. These are some instructions that you can refer to, and all this material is there on your CD for reference, and it's also available on the websites, numerous websites. These are some dependencies. So sometimes if you are running, say, Red Hat, you might need to upgrade a Tickle TCL or TK library, or you download a different version of GCC. So these are some heads up instructions that we wanted to give you. You might need to upgrade to make 3.0 or 3.8, depending upon what your enterprise version of Linux is. And similarly, all these are package dependencies that you might need to want to watch out for. And anytime there is some kind of question and there is a technical issue that you're having, we have something called the Developer Works forums. A lot of people, game developers, university faculty, researchers, cell developers, Linux kernel folks visit these sites, also actively monitored by IBM cell developers. And so you can post a question over there, and you can definitely expect to get some response. Again, the installed components for x86 platforms and PPC64 platforms, this is some information. This list of RPMs in SDK 2.0. These are all for your reference, so that you can anytime pull up your CD and refer to this. Very easy way of uninstalling. And Cell SDK is the install script basically. So all you need to do to install the development kit is download the ISO file. There's one place on Developer Works where the ISO file is available. Download the ISO file, run the script with the install option, and that's it. Your development kit would be installed. And again, clear instructions for installing the Cell IDE is also here. The makefile environment, the development kit comes with a standard makefile environment. We will go over that in the afternoon also, but basically there is a set of default makefile structures that you can use. A standard base level makefile, any application, say for example you are writing a simple application to do DMA transfers, there will be a standard base level makefile, and there will be two directories. For the SPU code resides in one directory and the PPU code resides in another directory. So the SPU code will have its own makefile because it's a completely different architecture. So there cannot be one makefile for both kinds of both processing units. So there's another makefile for the PPU, and so ultimately the final binary that you get, the SPU binary executable is embedded in the PPU binary, and they're all clubbed to be one binary. So that's all you need to run on the system simulator or a cell blade. And again, there's environment variables to switch the compilers from GCC to XLC and back. And in it, like a typical makefile, there's a make.footer and make.header with all the standard environment variables. A lot of times, and usually this happens a lot in real applications, is that you cannot use those default makefiles. You can write your own makefiles in that case. Okay. These are the environment variables to switch the compilers. Make.env is at the top level of the development kit with all these variables defined, and you can change the values either in the make.env file or in the command prompt. You can do a export PPU underscore compiler equals XLC to switch from GCC. And in order to, if you are using the standard default makefiles that come with the development kit, it's recommended that you export this variable cell underscore top. This is used in a lot of sample programs. So if this variable is not set, it won't be able to find the header file locations. So do export this value so that when you do just go to the samples directory and do make, the path is all visible to the make files. And these are the standard makefile variables. Program underscore PPU defines what is the name of the PPU executable. If it's a 64-bit executable, accordingly use the program underscore PPU 64 variable. Library underscore embed, it basically creates a linked library from an SPU program, as it says, to be embedded into the final PPU executable. And this is done, and I want to go over that later on when we go over the basic programming concepts, because we want the variables that are there in the PPU executable to be visible to the SPE and vice versa. So that's why we came up with something called CSOF, cell embedded SPU executable format. So basically, whenever in a PPE application, it creates a global reference that will be the same executable name for the SPE executable. So because of this global reference, anything that's there in the SPE environment will be visible to PPE. So it's possible to basically move data back and forth. And again, we'll see that via program code and additional diagrams in the next presentation. This is a sample makefile for a project. So if there's a sample directory, sample is the directory where your code will exist. There will be an SPU directory with the two, say for example, the sample code name is sample underscore SPU. Makefile will look like that. Program underscore SPU will define the sample SPU name. Library embed will create the archive file, and include path will give the link to the include path, and include the make.footer from the standard makefile environment that comes with the development kit. And similarly for the PPU. Now if you see in the PPU directory, there is a variable called imports, which will be linking with the archive file, that is there in the SPU directory. So this is how it embeds this SPU, the sample SPU, with the final sample executable that is produced as a result of the compilation. So finally, what's run on the simulator or a cell blade is this sample file, but it's got embedded in it the SPU side of the executable also. So the Linux kernel support is similar to traditional Linux support, just a few differences. For example, let's see. a few similarities and few differences, obviously. The PPE's Linux kernel is similar to Linux on Power, and as Duke went over this morning, the PowerPC core is based on PowerPC 970, but it's a really stripped down version of PowerPC 970. One of the reasons that it is stripped down is basically to save on the cost and the heat, the power factor, and simplify the hardware in general, so that while we're doing this ascent on performance, the heat is the wattage is low. So cell, I believe, is 32 watts, which is pretty good compared to what the market standards are. So the Linux kernel basically has support for virtual memory, including and there's a diagram coming up later on that will explain this effective address space versus the local store address space. It has support for large pages. By default, it's 4K in general, just like it is usually. But however, you can turn on large pages support using the huge TLBFS command. I think you can go up to 64 KB, 1 MB, and maximum you could go is 16 MB. So PPE code can create something called a Linux task. So in a way, you can split the application can split can create different Linux tasks, and these tasks can in turn create like an SPE thread. Now the SPE thread is nothing but just a group of data with its own main program, and once you create the thread, it just runs asynchronously. So you have the PPE has no control once the SPE thread is created. And it has a unique identifier, just like you would create, just like a normal P thread. And again, all these SPE threads can be created in one group. So in other words, you can create all these SPE threads and assign them to one group. So you can query status on that group on completion of a particular task. And each SPE thread has to belong to at least one thread group. And this is a table, again, it's from the programming handbook, which basically defines how when we're saying Linux thread versus SPE task or SPE thread, how is it different? Basically, Linux thread is just a thread running on the PPE Linux OS. The cell broadband engine Linux task is just a personalized way of saying that yes, this is my task. It can create 2 or 3 SPE threads, and so it's just basically modularizing your application to a certain extent. Now the SPE thread has its own environment. Again, once the thread is created, it uses all the resources it has got available. It has got its own program counter. It has got its own memory flow controller, which has a DMA controller inside it and a channel interface to send messages back and forth from the PPE to the SPE. And then there are some synchronization commands for communication between SPE to SPE. It has got its own 128 entry 16-byte register file. And MFC command queues are nothing but just queues where you can queue in DMA commands. So that's a very neat feature, that if you have to issue 3 or maybe 10 DMA commands at one time, they can be queued. So PPE versus SPE comparison, let's look at a few differences. Both of them have SIMD operation support. Single instruction, multiple data. In the presentation this morning, there was a chart which showed the way the data is laid out. When we talk about vectors, vector is nothing but just a bunch of consecutive memory locations. So in other words, if we have an array of say float A4, so it's 16 bytes of memory. So instead of saying float A4, you would say vector float A. So that's basically equivalent to a float 4 times 16 bytes. So it's just it's just a name given to address 16 bytes of consecutive memory locations, and there's no difference the way they are positioned in memory. It's same as a scalar. It's just that when we define a vector and you try to load a vector, it loads 16 bytes at a time. That's where the benefit comes, because compared to scalar programming versus vector programming, you're not doing 16 or 4 loads. That itself gives a huge benefit, because the load, the fewer loads and stores you do, the better. So instead of if you're doing a computation on say 16 bytes of data, in a normal scalar program you would do 4 loads. Okay. So both SPE and PPE have SIMD operation support. So they have their own VMX instruction set. VMX is Vector Multimedia Extension. This is something that was created with traditional PowerPC architectures. IBM is one of the foremost, actually it is the foremost to do multi-core technology. Initially it did the 2-core Power 4 that it released was for the first of its kind in the industry. So and this is just the cell broadband engine, and that's the reason Sony and Toshiba, came to IBM. That yes, you're the chip guru. If you think about the gaming consoles, Nintendo, right, is an IBM chip. Microsoft Xbox is an IBM chip, and finally, cell broadband engine is an IBM chip. So for cell broadband engine, we are using the standard VMX instruction set. So the PowerPC unit does have the VMX instruction support. Some of the instructions from traditional PowerPC 970 may not be supported, but a lot of them are. Let's see. So SPEs have a different kind of vector instruction support available, and again we'll be going over some of those instructions very soon. And because they are so different architecturally, they need different compilers. So PPE has 32 SIMD registers, whereas SPE has got 128 16-byte wide registers. SPE has got a unified register file, whereas PPE has got different registers for handling fixed point computations, floating point arithmetic, vector multimedia registers. Load latency in PPE is variable because there's an L1 cache and there's an L2 cache, and then there is the main memory. So any load operation cannot be deterministic, because you don't know where it's going to come from. It's going to come from the caches. Will there be a cache miss or a hit? So we don't know. Versus SPE is a very deterministic environment. No exceptions, no caching, very simple. So in other words, just to computationally calculate the performance number for any given application, it's very straightforward. You can, in theory, construe what the performance number will look like. SPE is currently optimized for single precision float. PP does not have double precision floating point support. Let's see. Currently, the single precision floating point support is very good, over 200 gigaflops. The PP is also good, comparable to the other platforms. But it's not. It doesn't give as good a scale up as single precision yet. We have a roadmap. We're working on the next few years. We will have better double precision floating point performance. As of now, it's just comparable, but we cannot boast off with a 30x or 20x performance benefit when it comes to double precision applications. Again, this is a table. Most of the data types are supported. Unsigned char, signed char. It's just that every variable will be preceding the word vector in it. So in other words, vector unsigned char will be having 16 bytes of data in them. So when you create a vector unsigned char, keep in mind that you're creating 16 consecutive bytes in memory. Similar unsigned long support is there, int support, double, standard data types are also supported on SPEs. It's just that when we say vector unsigned short, it is 4 short variables in that vector. When we say vector unsigned char, it's 16 bytes of scalar data types inside that one vector. When we say double, it's 2 double variables inside that vector. And these are the language extension. When I say language extension, it's just a different API instruction set that you have to use if you want to convert a scalar application to vector application. This is the communication part. So there is 3 different mechanisms by which you can communicate to the SPE. Take a real world example. You have your main program that you have built on the PPE, Now there is these data buffers that you need to move over to the SPE to do some really rigorous computation. So in order to send this data from the PPE to the SPEs, we have something called DMA. It's just nothing but doing a simple command which says, from this effective address in the main memory, send in these many bytes over to the local store in this SPE. SPE 0 through N, 0 through 7. So pick an SPE, send these many bytes. So once those bytes are there, do the computation on the SPE, do MFC put, memory flow controller underscore put. So once that data buffer is used, put those results back in main memory. Sometimes what you could do is do something like shared IO buffers to save the buffer space. When you send a buffer of data to the SPE, once the results are computed, you overwrite that buffer and send it back to the PPE. And so when we're using things like this, there comes a need of synchronization. Sometimes you want to know if a particular section of data from the main memory has already done some task. So another SPE might be dependent on stage 1 of image processing, or it's trying to do something on a particular data set, and say SPU N cannot even start until that stage is done. So then there needs to be synchronization variables or mailbox messages. A mailbox message is nothing but a simple 32-bit message that you can send over a channel interface to the SPE to say, I'm done. And then you can trigger off the next stage. There's 2 mailboxes. The SPE write outbound mailbox. Whenever we say write or read or inbound or outbound, the reference point, or get or put, the reference point is always in SPE. So if I say put, it means putting from the SPE into the main memory that the PPE is seeing. PPE does loads and stores from the PPE. The way it accesses main memory is by load and store from the main memory over to the register file that it has. The SPE has access to the main memory only via DMA operations. So in other words, SPE cannot do load and store into the main memory directly. It needs to get the data from the main memory into the local store and then do an instruction fetch. There is something called signal notification channels. You can configure them to be atomic. And this illustrates what I just mentioned. When we say get, it basically means transfer data into an SPE. So get into the SPE. When we say put, we mean putting the data back to the PPE. And this is a storage domain. This puts it all into perspective, whatever we have discussed so far, right? So here is the PPE. It has got its own processing units, and it has got its own register files, and here is the the DRAM memory, right? And this is one typical SPE. So the SPE is nothing but a combination of the SPU. SPU has got some processing units, the arithmetic processing units, and a combination of local store, which is just flat memory, 256 kilobyte flat memory. So it is single ported flat memory. So it's only one read-write port. So all the loads and stores, DMA operations and instruction fetch all happen through that one port. My mouse. So the way the PPE communicates, this is the EIB, the element interconnect bus, very, very high bandwidth bus. This is a great asset to this whole architecture because this is the bus that makes it possible to use cell in a cluster environment, form the basis of all these supercomputing nodes. So let's see, and it's a fully coherent bus. The whole DRAM memory is fully coherent. So and the way we implement coherency in memory and bus is via the SNOOP protocol. So the way the PPE communicates with the SPE is by writing to these memory mapped IO registers. So it does reads and writes to these memory mapped IO registers to send or receive data. The way the SPE sends data to the PPE is by writing to this DMA, to this memory flow controller via channel commands. So this is the way the SPEs communicate with other SPEs, and the PPE communicate with other SPEs also. So PPE just directly does load and store from the DRAM memory. The SPE will have to do a DMA operation, get the data into the local store, and then read it from the local store. So local store is 256 kilobyte, ECC protected, single ported, non-caching memory. The instruction prefetches are 128 bytes per cycle. Data access bandwidth is 16 bytes per cycle, and all loads and stores on the PPE or the SPE have to be aligned on 16 byte boundaries. If it's not aligned on 16 byte boundaries, there won't be a trap, there won't be anything. It will automatically truncate the last 4 bits. So, it will force it. So it is just automatically enforced. So we really recommend there's attributes as macros that we can use to our benefit when we're writing the code or defining an array that will automatically define it, on a 16 byte boundary. So quad word is 16 bytes in this case. A word is 32 bits and a quad word would be 16 bytes, which is the size of one cache line request. All cache line transfers are on a 128 byte boundary, and all loads and stores are on a 16 byte boundary. So they have to be aligned. If there's a DMA transfer that's going on, it has to be aligned on a 128 byte cache line boundary, and if it's a load and store, it has to be aligned always on a 16 byte boundary. And again, SPU can only fetch instructions from its own local store, and obviously there's no address translation. There is the privileged software on the PPU can set up effective address aliases to the local store.